Alright, so we're doing a quick video review of Boyle's law before we jump in and look at some new gas laws today, and we'll be doing some graphing again with the graphing calculator. So Boyle's law we explored yesterday was the first of the gas laws. We know that there's 4 variables involved in these laws: pressure, volume, temperature, and moles or amount of gas. In any one of the gas laws, we take 2 of the variables and then we explore how they relate to each other while the other variables are held constant. So in Boyle's law, we're looking at the relationship of pressure and volume. Robert Boyle studied this relationship, and he found that, as we did in our little experiment yesterday with the pressure sensors, that there's an inverse relationship between volume and pressure. Inverse relationships mean that in this case, when the volume, when the pressure, it says, increases, the volume would decrease proportionately. Or if the volume were to increase, the pressure would decrease proportionately. So when one goes up, the other variable drops proportionally by the same amount. Now, mathematically, you can write V is proportional to 1 over P, or you could say P is proportional to 1 over V. It doesn't matter how you write that. But to make the proportion into an equation, we throw in a constant. So in this case, V will equal K over P, or K times 1 over P, like that. Writing it as K times 1 over P lets you see more explicitly that what we have is really the equation of a straight line, where V is the y value, K is the slope, and 1 over P is the x value. So y equals mx, V equals K times 1 over P. Now when we did it yesterday, we wrote it as P equals K times 1 over V, which is essentially the same idea. If you solve the equation for the constant, you'll get P times V is constant. So in an inverse proportion, the product of the 2 variables is always going to be the same number, constant, and therefore P1 times a V1 will equal P2 times a V2. And again, that's true only if you're holding temperature and moles of gas constant. Now, besides these algebraic representations of the inverse relationship, you also need to understand the graphical relationships. If they're inversely proportional, then a graph of pressure versus volume would be a hyperbola. And if you graph pressure versus 1 over volume, as we did yesterday, you'll find that gives you a straight line graph. All right, let's take a look at the second law. The second law is called Charles's law. There's a bit of a typo in this title. Okay, so Charles is his name, and Charles's law is the name of the law. So it should really be Charles apostrophe S. In this animation, we're going to again record data like we did yesterday. Except yesterday we did it using an actual pressure sensor in the LabQuest. Today we'll do it with an animation. So we're going to explore how volume and temperature are related. So those are the 2 variables in Charles's law. More precisely, it's volume and absolute temperature. So we're using the temperature scale called the Kelvin scale, in which there are no negative temperatures. That's very important for Charles's law. So it's a temperature scale where the lowest possible temperature is called absolute 0, and so we give it a value of 0 Kelvin. And then from there we warm up. At room temperature, 25 degrees Celsius, on the Kelvin scale, that's 298 Kelvin. So 298 is what's shown here on the animation screen. We have a heating block below a gas which is held in a syringe. What I'm going to do is slide the slider on the heating block to cool the gas or to warm it, and then we'll see the volume change. I'll also display a data table so that you can copy down the temperatures. You can create this table yourself. Temperatures in the first column, and they're measured again in Kelvin, capital K, and then volume in the second column, and those volumes are going to be cubic centimeters, or if you prefer, milliliters. So let's start. I'm going to slide the scale temperature down to a low temperature. It doesn't really matter. Why don't we just take this one. Now, what we're seeing here is simply that as I'm cooling down from 298 down to 136 Kelvin, you can write that temperature down in 136 Kelvin, you can see the syringe plunger is dropping, and that's what we're seeing on the graph. What I'm looking for is the final volume. So what's the volume when the temperature reaches 136? You can see the current temperature here is dropping, and we're almost at there we are. We've reached the target temperature. So now if I close this graph and show the data table, you can write down the first data point. So 136 Kelvin and 11.9 cubic centimeters. Later we're going to want to copy this onto our graphing calculators. So 136 and 11.9 cubic centimeters. Now let's go and do a second point. We'll warm up the gas. We'll go to 166 Kelvin. The gas warms up. It's now reached that temperature, and we can see that the volume is now 14.5 milliliters. So again, be sure you're writing down these numbers in your table. We'll continue to warm up. We'll go up to 216 Kelvin. So the gas is warming up. You can see the current temperature is rising. There we go. We've reached the 216, and the volume is now 18.8 milliliters. We'll collect about 3 more data points. Whoops, as I just went back there. We'll collect three more data points maybe. So 264 Kelvin will be the next one. And we're almost there. And so the volume is now 23.0 cubic centimeters. And now let's warm up 315 Kelvin. Remember that 298 would be room temperature, 25 degrees. So we're now getting up to a reasonably warm temperature. So 315, the gas is now 27.5 cubic centimeters. Maybe a couple more data points. Let's go up to 367. Okay, 367 Kelvin. And the volume is 32.0 cubic centimeters. And we'll do one last data point here, 409 Kelvin, and the final volume is 35.7 cubic centimeters. All right, so now that we've got the data recorded, let's see if we can remember how to use our graphing calculators. So I'm going to open up here a simulation of a graphing calculator. Okay, if you can follow with me here with your own calculator. So I'm going to turn it on, and I'll clear whatever's on the screen. So I want to enter these data points. So you remember we go to the Stat button right here in the middle of the calculator, and we choose Option Edit. So if you know what you're doing, just go ahead and work ahead. If you want to follow with me, go for it. So I'm going to press Option 1, Edit. And I have no numbers already in my lists. If you have yesterday's values here, put your cursor up on top of the L1 symbol, press the Clear button, and then Enter. And that will delete all the numbers in that list. Go to the list 2, move your cursor to the top on top of the L2 symbol, press Clear, and then Enter, and that will delete everything in list 2. So do that until you've got clear lists like this. Now in list 1, let's enter our temperatures. So my first temperature was 136. My second one was 166. Okay, just keep going, entering your temperatures. 216, 264, 315, 367, and 409. So I've entered all of the temperatures in the first list. Now go to your second list and enter your volumes. I'm going to just use the 1 decimal place again. So 11.9 milliliters, 14.5 milliliters, 18.8 23, 27.5, 32, and 35.7. It's very important that you have the same number of data points in each column, so double check that you didn't miss a data point here before we go on. Alright, so hopefully you've got all of your data entered. If not, pause the video and wait until everybody's got the data recorded. So now we want to go and make a scatter plot. We want to make a graph of this data. So we press the second function button and we go above the y equals to the stat plot menu. And now of these plots, one of them may be turned on, so you can turn that one off if it's already turned on. I think yesterday we had plot 2 turned on, so I'm going to go to plot 2 here. If it's turned on, then just turn it off if you want right now, and then go up to the top and select plot number 1. Okay, it doesn't really matter which plot you use. If you want to use plot 2 because it was turned on, that's fine. Okay, but I'm going to use plot number 1. So I'm going to start by turning it on, and then I'm going to leave the type to be the first type that's selected. That's a scatter plot. I'm going to graph on my X list. That'll be my temperatures, which are in list 1, so I don't need to change this. X list is L1. And my Y list is going to be the volumes, which is in list 2. So I'm actually good to go here, list 1 and list 2. If you needed to change one of the lists, suppose your X list is not L1, it was L3, then you'd say second function and then go to L3 above the number 3 on the keypad, and now it's changed to L3. Okay, I actually wanted it to be L1, so I'm going to go back there and change it back, delete to L1. Alright, so now I'm got it set up properly. Do you remember what we want to do next in order to see the graph? Okay, we do not simply press the graph button, because the window settings will not be what we need, right? So the slow way to do that was to press the window button and then change all these window settings to make them work for our graph, to know what the minimum and maximum is for our temperatures, the minimum and the maximum for our volumes. We can manually change it. But we said yesterday we're not going to do that. Instead, we're going to cheat and just make the calculator do it for us by pressing the zoom button. So in the middle, press the zoom button, and then option number 9, if you scroll down, option 9 says zoom stat. We're making a stat plot, a graph called a stat plot. So zoom stat will set the window settings perfectly to see our graph. So just choose option number 9, and there's the graph. And I can tell right away that we have a direct proportion because it forms a perfectly linear situation. So I want you to take this and pause the video. You're going to sketch this graph. So like we did yesterday, in your sketch, be sure you label the axes. So we have volumes on the y-axis, we have temperatures on the x-axis. Indicate the units in your graph, in your sketch. The volumes are in milliliters, and the temperature is Kelvin, capital K. Put down the minimum and maximum values on each axis. You can see what they are by just clicking the window button. For me, the X values go from about 109 up to 436 Kelvin, and my Y values go from about 7.9 up to about 40 milliliters. So choose, make sure you indicate the minimum and maximum for both the X and the Y axes. Then roughly plot your points. As you see here, we had 1, 2, 3, 4, 5, 6, 7 data points, and I plotted them to form a straight line. Now you can indicate beside this that this means we have a direct proportion, and we'll see what that means in just a moment. But let's now go get the equation of the line through these data points. If you were here in slot B yesterday, we did this together in class. If you're in slot E at the end of the day, we didn't do this yesterday in class, so pay close attention. So I'm going to find the equation of the line that goes through this data, and then we're going to graph that equation so that a line goes right over the data points. So let's press the Stat button again, and we want to go this time to the Calc menu, which is here in the middle. So I'm going to press the right arrow to go to the Calc menu. What we want to do is called a regression analysis, and you can see there's several types of regression. Starting at option 4, linear regression, lin-reg, is when you have data that looks essentially like a straight line and you want to know the equation of the line. So that's linear regression. Option 5 says quadratic regression, quadreg. If your data looked more like a parabola and you wanted to know what's the equation of the quadratic function that describes the parabola, you would do a quadratic regression. And if your graph looked more like a cubic graph or a fourth degree, a quartic graph, etc., you can do different types of regression. Because our data looks like a straight line, we're going to do option number 4, which is linear regression. So I'm going to choose option 4. Now, right now, some of you are going to have a newer TI-84 calculator, and when you pressed lin-reg, it's going to show you a menu here. And among the things on this menu will be something that says XList, something that says YList, and something that says regression equation, REGEQ. Store regression equation. So you're going to listen carefully to how I'm going to describe how to do it here, and you're going to just translate that to your own calculator. So if this is what you see now on your calculator, you're going to tell the calculator to do linear regression on the data in our XList. Now our XList was in list 1, so second function L1. Then we're going to press the comma button, which is right above the number 7 on the keypad. And we're going to tell it where the Y values are, where the Y list is. So second function L2. If you're using the newer TI-84s with that menu, then you just told it that the X list is L1, and you've told it that the Y list is L2. Let's put another comma, because we're going to also have the calculator graph the equation of the line for us. So put another comma. If you have that menu with the TI-84s, the newer ones, there's no comma. You're going to go down to the store regression equation option, and then you're going to press the following. So variables, vars, which is right beside the clear button. So vars, variables. You're going to go to the right to the Y variables. You're going to choose option number 1, functions. And then any one of these functions will be fine. I'm just going to use the first one, Y1. So again, with those of you with the newer graphing calculators, you're telling that you're doing exactly what I just did in the store regression equation. You press the vars button, you go to Y variables, then functions, and then choose Y1. So what we're about to do is tell the calculator to perform linear regression, which means to find the equation of the line of best fit for the data where the X values are in list 1, the Y values are in list 2, and then graph the equation as Y1, the first function. So press Enter. Those of you with the newer calculators, move your cursor to the Calculate button and then say Calculate. So here's the equation of our line, y equals ax plus b. So the a is our slope, 0.0872. The b is our y-intercept. Now technically the y-intercept should be 0, and it's very, very close to 0 here, 0.0095. There was a rounding error and things in our recording of the data, so it's not perfectly 0, but it's very close to 0. If you press the graph button again, so go ahead and do it, press the graph button, you'll see that now you have your original data points with a line going through them. That's the line that we just saw. If you press the y equals button, you'll see that the calculator has graphed that equation that we just saw in the in the first function, y1 equals, and it looks rather messy with a whole bunch of extra digits. If you want, you can clean it up. Delete all the numbers before the x symbol. Just delete them. Okay, I'm going to keep maybe 3 of those digits, so I'll keep 0.0872, and I'm going to delete all these numbers except for the x symbol. Leave the x alone. And then plus, it's supposed to be a 0, so I'm just going to delete everything after the x. So I'm pressing the DEL delete button. Okay. So there's a cleaner looking version of the equation, just y equals 0.0872x. If I press my graph button, you'll see that the graph essentially looks the same. Now you can write this equation, you can draw the line like this through your own data in your notes and write the equation that we just saw, or whatever your calculator said the equation was, beside that. So 0.0872x. Instead of saying y and x, if you want to be a bit more clever, you know that on our y-axis we actually have volumes, and on our x-axis we have temperatures. So instead of y equals 0.0872x, you could say v equals 0.0872t. That would be a better way to do it. It would translate it from generic math into the chemistry. Alright, so there's a review of how to graph with the graphing calculator and how to do linear regression as well. Let's just go back and wrap up these notes. So we've done the experiment. Let's summarize what we've discovered. So Jacques Charles is the name of the Frenchman who investigated this originally. He discovered that volume and absolute temperature have a direct relationship between them. Okay, they vary directly. The absolute temperature means the Kelvin temperature scale. Again, that means there's no negative temperatures involved. If you find that I'm going a bit too fast here, feel free to pause the video so you can write stuff down as needed. To say that there's a direct proportion between temperature and volume means that we can say V is proportional to T, or if you like, T is proportional to V. And to change that into an equation, we just put a constant in. So V equals KT. That, of course, looks like the equation y equals mx, and that explains why our graph of V versus T was a straight line. If you rearrange the equation for K, you'll get K is equal to V divided by T, which means the quotient, V over T, is constant. So therefore, a V1 over a T1 will equal a V2 over a T2. And that's true if pressure and moles of gas are held constant. It's also true only if you're using the absolute temperature scale, the Kelvin temperature scale. The volume units don't matter. As long as they're the same on both sides, you can use milliliters, you can use liters, you can use cubic centimeters. As long as the volume units are equal on both sides of the equation, no problem. But the temperature units must be Kelvin. Okay? There cannot be any negative temperatures, and you can't have a 0 as a temperature in this equation. Otherwise, you'd be dividing by 0, and that would be a problem. Okay? All right, so there's Charles's law, and as we saw, Boyle's law. Let's just quickly talk about absolute temperature and what it actually means. So, absolute temperature. We usually think about temperature as just meaning how hot or how cold something is, but that's actually rather imprecise because temperature has a much more specific meaning. The absolute temperature is a measurement of the kinetic energy of particles, of gas molecules and atoms. Kinetic energy is the energy of motion, the energy of movement. Anything that's moving has a velocity, has a kinetic energy. The faster it's moving, the more kinetic energy it has. So temperature is a measure of kinetic energy. Look at the equation. kinetic energy is 3/2 RT. The R here is called the ideal gas constant, so it's just a constant, and the T there is our absolute temperature. So the temperature is the only thing, the only variable which determines kinetic energy. We're going to talk more later about that ideal gas constant, the R. If the temperature drops, then kinetic energy drops, and that means particles have less kinetic energy. They move more slowly. Eventually, if you cool down enough, motion will stop. The velocities slow down until they stop. At that point, if there's no more motion, then you've reached the lowest possible kinetic energy, and therefore you've reached the lowest possible temperature. This lowest temperature is called absolute zero. It's a theoretical point because we can never actually reach that temperature in the lab. We can get very, 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 very close, but we've never actually been able to get to it, and we won't ever be able to, because to measure the temperature, to see if we've reached absolute zero, we have to put some kind of device in to measure the temperature. And as soon as we do that, some heat will flow into the system as well, and that means it's not going to be at absolute zero. So absolute zero is a theoretical temperature. It's not something that we can actually achieve in the lab, although, again, we've reached very close to it. I think within billionths of a Kelvin. The relationship between Kelvin and Celsius is relatively simple. The Kelvin temperature is just the Celsius temperature plus 273.15. So by that logic, if 0 Kelvin is the lowest temperature you can have, you can see from this equation that that will translate into a Celsius temperature of negative 273.15 Celsius. So negative 273.15 Celsius is absolute zero on the Kelvin scale. 25 degrees Celsius would be 298.15 Kelvin. All right, so you can use this little equation to convert Celsius and Kelvin back and forth. Two other laws, which we're not going to go into the same depth in terms of investigation. We're just going to take some notes on them. One is called Avogadro's law, which is a relationship between the amount of gas, moles, and the volume of a gas. Now, if you just stop and think about this, I think you'll agree it's rather obvious now that we know that there must be a direct or an inverse relationship. If you put more gas into a balloon, more moles of gas, none of us would be shocked to see the balloon get larger. So moles and volume must fall into a direct proportion, which means a graph of moles and volume would give me a straight line graph. Mathematically, then moles, volume divided by moles is going to be constant, and V1 over N1 will equal V2 over N2, okay? Since V equals K times N in that situation. Pressure and temperature are held constant when you're investigating Avogadro's relationship. The last of the major gas laws that we'll study in this first part of the gases unit is called Gay-Lussac's law. Gay-Lussac studied the relationship between the absolute temperature and the pressure of a gas. If you imagine having a gas in a sealed, rigid container, so nothing can get in or out, and you heat that up, what's going to happen, right? If you're heating up a sealed container, you're in danger of having it explode. It may explode because the pressure inside is going up. So when you heat it, the particles move faster in the container, and if they're moving faster, they collide more often and with more energy with the walls of the container, and that creates greater pressure. So temperature and pressure are directly related. Since they're directly related, we get the same mathematics as Avogadro's law. P over T is constant, so P1 over T1 will equal P2 over T2. P equals K times T, a graph of pressure versus temperature will be straight line. And this is true only if you're holding the moles and the volume of gas constant. So those are 4 basic gas laws: Boyle's law, Charles's law, Avogadro, and Gay-Lussac. You're expected to know the names of the laws, the variables involved, the variables that are held constant, whether they're direct or inverse relations. You should know the algebraic interpretation of each law, and you should be able to understand something about the graphical interpretations. So, for example, if I tell you that if I mention Avogadro's law, you would know that that's moles and volume being studied. It's a direct proportion, so V equals K times N. V over N is constant. V1 over N1 equals V2 over N2. V versus N, a graph, would be a straight line graph where the slope is that constant K. That's what you would need to know for each of those 4 gas laws. We'll stop there. We're going to be doing some problem solving on a web assignment involving the gas laws starting on Wednesday.